Today, we're tackling a problem that seems simple on the surface, shifting elements within a two-dimensional grid. But how do you perform this operation efficiently, especially for large shifts? There's a clever mathematical trick to convert this 2D challenge into a more manageable 1D problem. The problem, Shift 2D Grid, asks us to take a given m by n grid of integers and an integer k. We need to shift the grid elements k times. In each shift, an element at grid row I, column j moves to row I, column j plus 1. If an element is in the last column, it moves to the next row's first column. And if it's in the last row and last column, it wraps around to the first row, first column. We return the final grid after k shifts. A straightforward but inefficient approach is to simulate the shifts one step at a time. For each of the k shifts, we create a new grid and iterate through the original grid. Each element is placed into its shifted position in the new grid. After populating the new grid, we replace the original grid with the new one. This process repeats k times. While it correctly implements the shift, performing k full grid traversals means a time complexity of O of k times m times n, which is clearly too slow if k is very large. The space complexity for storing the new grid is O of m times n. The key insight for optimization is realizing that a 2D grid can be flattened into a 1D array. Once flattened, a cyclic shift is much simpler. We can map each 2D coordinate to a unique 1D index. For an element at row I, column j, its 1D index is I times n plus j. The total number of elements is m times n. If we shift this 1D array by k positions, a new 1D index can be calculated as the original index plus k, all modulo the total number of elements. Then, we convert this new 1D index back to 2D coordinates. The new row is the new 1D index divided by n, and the new column is the new 1D index modulo n. We declare a new grid and iterate through the original grid, calculating each element's new position and placing it directly. This avoids repeated full grid copies. Let's trace this with a 3x3 grid and a shift of k equals 1. The total elements are 9. We first reduce k modulo 9, so k remains 1. Consider the element at 0, 0, which is 1. Its 1D position is 0 times 3 plus 0, which is 0. Its new 1D position is 0 plus 1 modulo 9, which is 1. This maps to new row 1 divided by 3, which is 0, and new column 1 modulo 3, which is 1. So, 1 moves to 0, 1. Next, element at 0, 1, value 2. Its 1D position is 1. New 1D position is 1 plus 1 modulo 9, which is 2. This maps to 0, 2. This continues for all elements. The element at 2, 2, value 9. Its 1D position is 2 times 3 plus 2, which is 8. New 1D position is 8 plus 1 modulo 9, which is 0. This maps to new row 0 divided by 3, which is 0, and new column 0 modulo 3, which is 0. So 9 wraps around to 0, 0. After processing all elements, the final grid has 9 at 0, 0, then 1, 2, 3, and so on, with 8 at 2, 2. This correctly reflects a single cyclic shift of the entire grid, achieved in one pass. You'll spot this pattern when you need to perform cyclic shifts on a 2D structure, or when a 2D problem can be simplified by flattening it into a 1D array. Think about coordinate transformation whenever elements maintain relative order but shift their absolute positions, especially with wraparound behavior. The time complexity is O of m times n, as we iterate through each element of the grid exactly once. The space complexity is also O of m times n to store the new grid. This coordinate mapping technique is powerful. Try applying it to other grid-based problems. If you found this helpful, subscribe for more concise DSA explanations.